All right, good morning, afternoon, or evening, everyone. We're going to continue on with lecture number 28. So picking up from where we left off last time, we're still going to be talking about the Aldol reaction, and we're going to be talking about reactions of enolates. So the beginning of this lecture will be focused on how do we use this reaction in a synthetically useful way to build molecules. And so in the previous lecture, we saw some self-condensation reactions of aldols, and this allowed us to make important carbon-carbon bonds, either carbon-carbon single bonds or double bonds, depending on the temperature. And now we're going to look at what happens if we try to introduce two different components to the reaction. So here we see we have two different types of aldehydes. In one case, we have an aldehyde with a single methyl carbon, and another aldehyde that has two carbons next to the aldehyde. So if we put these all in a reaction together, and we're using 10% sodium hydroxide, so we know these are basic conditions, and we're at 5 degrees C, so we don't expect any of the over-alkylation or over-dehydration product, we would expect to make hydroxyaldehyde products. But as you can see, we have two different ways these molecules can react. So if we have this simple aldehyde, this will be in equilibrium with its enolate. This will be nucleophilic at carbon, and it potentially could react with itself. So if the two red molecules react together, this will give us the product at the top, this homodimerization. Similarly, if we have the one carbon homologated enolate, it is also nucleophilic at carbon to react with another aldehyde. This potentially could give another homodimerization product. But at the same time, we have yet another option where this enolate could react with the other coupling partner, or with this enolate reacting with the other aldehyde. So we end up with a mixture of both crossed and homodimerization products. So that in the end gives us 1, 2, 3, 4 different products in this mixture. And so trying to do selective aldols with two different coupling partners becomes a bit more challenging because you will get all combinations. There are some methods to use this reaction to react two different compounds productively. And one way to do this is to use non-enolizable reactants. So these are compounds that do not have an alpha hydrogen. This means they can't be deprotonated, so really we'll only be generating one enolate in solution. So we can see here on this benzene ring, there are no protons next to the aldehyde, so there are no acidic hydrogens to deprotonate. That means that this cannot homodimerize, and we can get a selective process going from the enolate that forms in this equilibrium. Sometimes the reactive aldehyde component could be added slowly to an excess of, slowly to the non-enolizable component to get better selectivity. And this will give us the expected aldol addition products in a similar fashion as before. So after we have proton transfers, we'd end up with a product like this. So potentially you could get some of this aldol product along the way. This would be the homodimerization product, but usually the reaction conditions we can tune to get a selective addition towards attack on the non-enolizable system. Another way to do this, instead of a benzene ring, it could just be a fully substituted carbon. This also doesn't have any hydrogens that can react. So let's say this one was even heated. That would now give us the full aldol dehydration product. That'll look like this. And sometimes you'll see other bases. So this is sodium carbonate. This will just be another base. Again, we're heated, But note that after you make this enolate, so we make our equilibrium, things like formaldehyde that have two hydrogens, these also cannot be deprotonated. They would not have any resonance stabilization if you tried to deprotonate those hydrogens. And after attack and reprotonation, we get this hydroxyaldehyde product. Note that since these are two methyl groups adjacent to the aldehyde, we cannot get, I wanted that to be orange. We cannot get the final elimination of the hydroxy, so it'll still remain intact. So also we need to have alpha hydrogens to eliminate water. And you can do similar things using ketones and aldehydes as well. Again, the coupling partners are going to have non-enolizable aldehydes. And this reaction is exactly the same as we've seen for aldol condensations on the slide before. The only difference here is now we end up having ketones, which means we have two carbons on either side of the carbonyl. Otherwise, this is going to be essentially an identical process. We'll be looking at the reaction temperature. We'll see that at 100 degrees C, we can expect to probably have an elimination product. So once again, this would go through first making the acetone enolate. This will go to react here. After it adds into the aldehyde with a proton transfer, we're going to get a hydroxy ketone out. And this will continue to be deprotonated at 100 degrees C. To give another enolate. And this enolate now just facilitates this beta elimination of water to give our final product. So again, this is absolutely not different at all from the aldol condensation. We're just using ketones. There's sometimes a slightly different name associated with this, and we'll see a number of different names for what seem to be quite similar reaction. So Claisen and Schmidt were the people that studied this. So here's a picture of Claisen. Note that once again, all these reactions took place a long time ago. And you also may be wondering, what about this methyl here? So depending on reaction conditions and number of equivalents, I'm going to make a phenyl just to make this abbreviated to fit on the slide. We could actually have this reaction take place one more time and end up with a double addition product. So to figure out whether this would happen, we can probably just say that we're going to have two equivalents of the aldehyde and one equivalent of acetone. That way you know that both of these reactions could take place. If you end up with a single methyl group, then we can only have a single reaction take place. And overall, a similar outcome will be observed, where we have the initial attack of the enolate onto the aldehyde, followed by loss of water through that E1CB, the conjugate base mechanism, where we do need to have this deprotonated intermediate take place as a discrete step in the mechanism. And so one thing you may be wondering about, what about the self-condensation of a ketone with itself? So this is an important thing to note. Ketones are less reactive than aldehydes, and the self-condensation equilibrium is generally unfavorable. So the reaction of a ketone enolate with an aldehyde will be quite a bit faster than the same reaction with itself. So I'll keep it as a phenyl for consistency. So this reaction we would expect now to be slow and probably will not be favored overall. So when you have a ketone enolate and an aldehyde, the ketone enolate will form quickly in equilibrium, and the aldol process will be quite a bit slower. And we can see a little bit of the reason why. That's because we're making now a fully substituted carbon here. It's more sterically hindered. And will result in an overall kinetically slower reaction. So this lets us use this productively where we can mix and match ketones with enolyzable groups and aldehydes without enolyzable groups to get these types of reactions to take place.